I have a tutorial here to review how the temperature at different locations in the protosolar disk varied with distance away from the forming sun. I'm going to be talking a lot about this plot, which is what the temperature of material was in the disk as a function of distance away from the forming sun. And this looks a little bit different than the plot that's in your textbook. This plot is it's called a log plot. So you can see there's the distance between 100 and 1,000 is not what you would say is proportional to the distance of doubling from 100 to 200. So this is the logarithm of the temperature and the logarithm of the distance. That's just why it looks like a straight line. So it's the same data, it's the same information, it's just presented in a different plot. All right, temperature and formation of our solar system. Consider the information provided in the graph and table below. The graph shows the temperature expressed in Kelvin at different distances from the sun, expressed in astronomical unit or just AU, in the solar system during the time when the planets were originally forming. The table provides some common temperatures to use for comparison. So sort of things you might know from everyday life, what room temperature is, or the temperature the water freezes, or human body temperature in Fahrenheit and Celsius. And then in the context of astronomy, we're just going to be using this temperature in Kelvin, which I'll actually say that should be a capital K. All right. So what is the temperature at the location of Earth? So 1 astronomical unit, about what does that correspond to on my y-axis? Just speaking roughly, it's about 600 Kelvin reading off from the graph. Mars's distance is right about 500 Kelvin. So both of those are above the boiling point for water. So which of the planets are going to form at temperatures hotter than the boiling point of water? And it's all of our inner ones there, the terrestrial planets. Mercury, Venus, Earth, and Mars. All right, so which of the planets formed at temperatures cooler than the freezing point of water? Water freezes 273 Kelvin, so that's about in there. So all of the gas giant planets. It's not an accident. That's where you find gas giants. Jupiter, Saturn, Uranus, Neptune. Alright, at temperatures hotter than the freezing point of water, light gases such as hydrogen and helium likely had too much energy to condense together to form the large gas giant Jovian planets. So over what range of distances from the sun would you expect to find light gases such as hydrogen and helium collecting together to form a Jovian planet? So it's going to be where it has to be cooler than the freezing point of water, which is around 2 AU. So for distances greater than approximately 2 astronomical units. Over what range of distances from the sun would you expect to find only solid rocky material collecting together to form a terrestrial planet? So if it is too hot for gases and hydrogen compounds to condense. The things that are solid are going to be rocks and metals, and those are what make terrestrial planets. And that is going to be in the inner solar system. So less than about, say, 1.5 AU. Is it likely that a large Jovian planet would have formed at the location of Mercury? Well, the temperature is above 1,000 Kelvin. Not just hydrogen compounds are going to be a gas there. You're going to have even a lot of silicates and rocky materials are going to be vaporized. So you just don't have enough solid material to make a Jovian planet at that high a temperature. So too hot to have that much solid material. All right, so we get a fair bit of insight into how our solar system formed by looking at what the temperature was in different locations in the protosolar disk as the solar system was forming. And we have a range where we have terrestrial planets made because in that region we had only metals and rocks that are solid. And then you go into the outer solar system where temperatures are below the freezing point from water, and suddenly, in addition to metal and rock, you have all of those hydrogen compounds. So things like water, things like methane, things like ammonia are going to be available as ices, and you suddenly have 10 times more solid material. You're able to form a larger solid core for like a proto-Jupiter or Saturn, Uranus, or Neptune, and then that has enough gravity to start accreting and holding on to a thick atmosphere of hydrogen and helium, which is what's most abundant in that protosolar neighborhood as the solar system was forming. But you have to have enough material to have a strong enough force of gravity to hold on to that.